So this is the lecture on electron configuration, which comes from information from chapter 4. You can see the pages listed here if you need to go back and reference any of this information. So we're going to start with different types of electron configurations. Remember that an electron configuration tells you the arrangement of the electrons in an atom. Where they are placed, you can think of it like a seating chart. It's where they are seated. Because low energy systems are more stable than high energy systems, remember that that is a law of nature. In nature, all things tend to go to the most stable state. Electrons tend to assume an arrangement that gives them the lowest possible energy level. We know this as the ground state. The ground state is when the electrons are as close to the nucleus as they can be, and this is when the atom is in its most stable state. And again, remember, atoms, like most things in nature, want to be in their stable form. The arrangement of electrons in this stable state, when the electrons are in their ground state, is called the ground state electron configuration. We're going to talk about a couple of principles and laws and theories that have helped figure out electron configurations. The first one is called the Aufbau principle. This is the principle that states each electron occupies the lowest energy orbital first. Again, nature always tries to take the easiest route. It's going to go to the easiest thing it can first. So electrons are always going to go to the orbital closest to the nucleus as they can get, or the orbital with the lowest energy. If that orbital is filled, then it goes to the next highest energy and so on. So the first step when writing electron configurations is determining the sequence of atomic orbitals from lowest to highest energy. And this is called the Aufbau diagram. So here's the diagram. This is in your packet. So no need to memorize how to draw it. All you have to know is how to use it. And remember, it's like following the yellow brick road. It's like following the arrows. So to get the order of the orbitals, you're going to go 1s, 2s, 2p, 3s, 3p. Now up until there it makes logical sense, but now you have to continue to follow the arrows. After 3p, you have 4s, 3d, 4p, 5s, 4d, and so on. You just keep following the arrows to get the order of the orbitals from lowest to highest energy, and this is the way the electrons fill. This is a graph showing you this same information. Again, it's showing you the order of the orbitals from lowest to highest energy. And you can see it goes 1s, 2s, 2p, 3s, 3p, and now things start to get a little disordered. The 4s is actually lower energy than the 3d. And again, this diagram tells you that, but this is showing you it in a graph form. Then we have 4p, 5s, 4d, 5p, 4f, etc. and so forth. So up here they get really jumbled. So remember, if you know how to read the Aufbau diagram, there's no need to memorize this, but this is showing you it in graphic form. Now the reason why this happens. Remember that all orbitals in the same sublevel have equal amounts of energy. So if we look at the lines, remember that each sublevel, again, can have like a different floor. The S sublevels have one floor. You can see every single one of them only have one line. The P's have 3 floors. Notice there's 1, 2, 3 lines. And this is where we get the 6 total because each one of these can hold 2. All the P's have 3, all the D's have 5, and the F's have 7. Each one of these lines within the 2p have equals amount of energy. Everything's equal. Sublevels within the principal energy level have different energies. So the 3 2p orbitals have equal energy, but the 2p orbital has more energy than the 2s. You can see that's higher in the graph. So each of these 3 orbitals is the same, and all 3 of them are higher than the 2s. So not everything in the 2 principal sublevel has the same energy. In order of increasing energy, the sequence is S, P, D, and F. S's usually have less than P, less than D, etc., and so forth. Sublevel orbitals in one principal energy level can actually overlap, and that's how you get the fill order being a little off. So you look here. This is all the same quantum number. We have 5s, 5p, 4d. But you can see the 4d and the 6s actually overlap here a little bit. The Aufbau diagram is used to determine the order of this orbital. So all this information, all the overlapping, all of the order from lowest to highest energy takes place using this diagram. Remember, if you just follow the arrows, you get the order of the orbitals. Each sublevel can only hold a certain number of electrons, and this is based on how many orbitals it contains. Think of it like floors. Remember that S has 1 floor, P has 3, D has 5, F has 7, and each one of these can only hold a maximum of 2 electrons. So if you multiply each one by 2, you get the total number of electrons that can fit in each of these levels. So for S, it can have a maximum of 2, P 6, D 10, F 14. It does not have to have the max, but that is the max. Once you've reached that maximum number, you have to go then to the next orbital. There's a couple of parts to the electron configuration. First is called the principal energy level, which is right here. It's the big number written in front. This tells you the amount of energy that the orbital contains. It also tells you the size. So the difference between a 1s orbital and a 2s orbital is that the 2s is bigger. The next is the energy sublevel, or the letter. Remember, that gives you the shape. S are spheres, P are dumbbells. You don't have to worry about the shape of D and F. And that also tells you the max that can fit there. Remember, an S can only hold 2. Doesn't matter if it's a 1s or a 2s, as long as it's the letter S, the max number of electrons is 2. P can hold 6, D can hold 10, F can hold 14. And finally, the superscript looks like kind of like a square root. A square is the number of electrons in that orbital. So if you think of it like an apartment, usually apartments have a number and a letter. The 1s, the 2s, the 2p, this is just telling you the apartment. The number up top, the superscript, tells you how many electrons or how many people live in that apartment. So when you're talking about how many electrons, really the big number in front and the letter have nothing to do with it. That tells you the location. It's the superscript that tells you how many. So for example, the electron configuration written here is for carbon. So we have 1s2, 2s2, 2p6. These three numbers, the principal energy level and the sublevel, tell you the apartment number. The superscripts tell you how many. If you add the superscripts together, it should equal the atomic number. Remember that in an atom's ground state, the number of electrons in its stable state equal the number of protons, which is equal to the atomic number. Of course, there are exceptions to this, or different ways of doing it. One different way is called the noble gas configuration. It's like a shorthand. What you can do is use the noble gases, remember they're in column 8A, as a symbol representing a configuration that comes before it, and then you can just write the things that are outside the symbol. So for example, if you write HE in brackets, that means you have a 1s2. That's actually telling you there's 2 electrons in this configuration. Not that helpful when you get to neon, however. Neon in brackets represents this whole configuration. So this takes care of 6, 7, 8, 9, 10 electrons just by writing it like this. The way you finish the noble gas configuration is you write the configuration for everything outside that comes after this bracket. So if we look at the example here and we look at sodium, magnesium, aluminum, and silicon, they go right in order, 11, 12, 13, 14. So with configurations, electron configurations, you're really just adding an electron to the last principal energy level. So if we look here, we have 1s2, 2s2, 2p6, 1s2, 2s2, 2p6. 1s2, 2s2, 2p6. They all have that configuration within it, and then they're just adding one to the end. This configuration, 1s2, 2s2, 2p6, is the electron configuration of neon. So if you take this and cut it off after the 2p6 and you write neon in brackets, this represents up until the 2p6. So you don't have to write it. You can just start with everything that goes from that, which in this case is going to be the 3s1, 3s2, 3s2, 3p1. So again, it's a shorthand version. The Pauli exclusion principle is another theory that helps us figure out these electron configurations. Pauli exclusion principle has to do with the electron spin. Electrons spin just like the Earth rotates around its axis, and when they occupy an orbital, they have to have opposite spins. This is what limits each orbital having only 2 electrons on it. An arrow pointing up represents an electron spinning in one direction, an arrow pointing down represents the electron spinning in the other. And what the Pauli exclusion principle says is you can only have 2 electrons per orbital because they have to have the exact opposite spins. Now, they're not necessarily spinning up and down. They could be spinning at any angle, but they're spinning in exact opposite directions. And this is why you have to have 2. You can't put a third in there. There is no other direction for a third one to go. If an orbital has two, what we call paired electrons. It's filled. There's 2 electrons in there. They're going to have opposite spins, and you're going to write that with a 1 up arrow and 1 down arrow. The way that you're going to use the arrows is in something called an orbital diagram, which is another way to show how electrons are arranged. For orbital diagrams, you're going to use either an empty box, or you can actually use a line as well. A box with a single up arrow means there's 1 electron, an up and down arrow means there's 2 electrons. Each box is labeled with the principal quantum number and the sublevel at the bottom. So you can see here, here's an orbital, 1s, 2s. And if you count the electrons, there's 1, 2 in this, 1, 2 in this. Notice you're supposed to write the up arrow first. Now, when we get to the 2p, remember there's 3 floors. There's 3 levels of the p's. So you're actually going to do 3 boxes and label all 3 the 2p. Now, Hund's rule gives us an idea of how these electron orbitals, these boxes, are filled. And due to the repellent charge, electrons are going to fill these orbitals in a specific way. I call Hund's rule the bus rule. If you're going to get on a school bus, you're immediately going to go to the back of the bus. That's almost like the ground state. The electrons are going to go as close to the nucleus as they can be. And also, generally, when kids get on a bus, they're going to try to sit in the seat by themselves. They're only going to double up once all the seats already have a kid sitting in it. So that's what Hund's rule says. Hund's rule says that single electrons with the same spin occupy equal energy orbitals before they go and pair up. So for example, with the 2p, there are 3 possible seats. Think about it like a seat on the bus. When the first electron comes in, it's going to go all the way to the back of the bus and sit by itself. Now when the second kid comes in, the second electron, it's not going to go and sit with that kid. There's 2 more open seats. It's going to sit by itself again. Remember, it's going to be pointing up. Third one again, it's not going to sit with these kids. It's going to sit by itself and pointing up. Now, when the next kid gets on the bus, there's no more open seats. Look, they're all taken. It has to go ahead and pair. It's going to go again to the back of the bus, and it's going to pair up. 5th one's going to pair up. 6th one's going to pair up. This happens only with equal energy orbitals. So S only has 1 orbital. It doesn't happen there. This happens with P, D, and F. It's going to fill up before it goes back and doubles and fills down. The kids are going to sit by themselves on the bus until they have to double up. The last way of showing how electrons are arranged in an atom is called quantum numbers. Quantum numbers is very closely related with an electron orbital. What you do is you pick a specific electron in an orbital, let's say this one, and you write quantum numbers describing where it is. There are 4 values, N, L, M, and S. Sometimes it's written as MS, M sub S. The first one, N, is the principal quantum number. This is the big number written in front of the electron configuration. This tells you the size and energy level of the orbital. N has a value between 1 and 7. So you're just basically going to write, if it's a 1s orbital, N is 1. So you're just going to write a 1. If it's a 2s, you write a 2, etc. and so forth. L is the shape, so the S, P, D, and F shape. The range of values is 0 to 3, or you can think of it as the principal quantum number minus 1. So what that means is the number value for an s orbital is 0. Then it just goes up from there. P is 1, D is 2, F is 3. The magnetic quantum number, M or M sub L, this is going to tell you when the equal energy orbitals are there, for example, the 3 P's, which P is the electron on, which D level is the electron on. And it's very simple. All you do is take the orbital diagram, you find the middle is the 0, and then it acts like a number line. Anything to the left of a number is negative, anything to the right is positive, and you just go up and down. The last letter is the spin orientation number, S or M sub S. This only has 2 possible values, a plus 1/2 and minus 1/2. When you write plus 1/2, the electron is pointing or spinning up. When it's minus 1/2, the electron is spinning down. So this is a summary of the 4 numbers. Remember, N is the distance or the size, L is the shape, M is the orientation in space, which one of the P's is it on, and S is the electron spin, is it up or down. When we get to more chemical reaction type stuff, really what we're only going to talk about is the valence electrons, because the valence electrons determine the chemical properties of the elements. These are the electrons in the outermost orbitals, or the ones in the highest principal energy level. So it's important that we take these arrangements of electrons and figure out which ones are on the outermost. If you think about it, when something bonds, it's not going to bond with the inner electrons, it's going to bond with the outer. And that's why valence electrons are very important. So we look at sulfur. Sulfur has a total of 16 electrons. When you write the noble gas configuration, remember neon is representing all the core electrons. Here's the ones on the outside. Notice it's the highest principal energy level, or the biggest big number you see. Notice you see a 3 here and a 3 here. These 2 electrons and these 4 electrons are both in the highest principal energy level. So to get the total number of valence, you add them. So there's 4 here and 2 here for a total valence of 6. Electron dot structures are a graphical representation of the valence electrons. You have the element symbol. This represents the nucleus and the inner or core electrons, as we call them, surrounded by dots that represent the valence. They're very simple to write once you determine the number of valence electrons. You start by writing the element symbol in the middle, and you use dots around the symbol to represent the valence. They can be placed in any order, meaning you can do top, bottom, left, right. You can do it around like a clock. You can do it around counterclockwise. It doesn't matter, but you may not pair up electrons until all 4 corners, like a cross, have been filled out, very much like Hund's rule. So if we look at the example here, lithium's atomic number is 3, so it has 3 total electrons. If you write the configuration out and you look and you see the highest principal quantum number here is 2. There is 1 electron in all of the 2's, so the valence is 1. Then to write the dot structure, you write the symbol of the element and 1 dot to represent the 1 valence electron. This dot can be on top, bottom, left, right. Usually it's on the top. Doesn't really matter though where it is as long as you only have 1. We do beryllium next for total electrons. Here's the electron configuration. We look again, there's only the 2s, the highest principal quantum number. There is 2 electrons this time in the 2s, so the valence of beryllium is 2. And notice I write a dot on the top and a dot on the bottom. The only thing I'm not allowed to do is do 2 dots on the top, or 2 dots anywhere around the core. And then go ahead and practice with this slide, writing the electron configurations for nitrogen and fluorine.